Welcome back to AI Paper Podcasts. Today we're tackling a really interesting question. Have we maybe been overestimating what reinforcement learning, specifically RLVR, is actually adding to the core reasoning power of large language models?
Yeah, it's a big question. There's this pretty thought-provoking new paper suggesting that a lot of the impressive reasoning we see might actually, already be baked into the base models themselves.
Okay, so which paper are we digging into today?
It's called Does Reinforcement Learning Really Incentivize Reasoning Capacity in LLMs Beyond the Base Model? It's from researchers at Leap Lab, Tsinghua University, and Shanghai Jiaotong University, dated April 25, 2025. And honestly, for anyone following LLM progress, it really challenges some common beliefs.
Right, because the narrative, especially with models like OpenAI o1, DeepSeek R1, Kimi 1.5, it's been that RLVR is kind of the secret sauce, hasn't it?
Exactly. The ingredient that pushes these models past their initial limits, particularly for tricky stuff like, advanced math or complex coding tasks.
The idea being that RLVR sparks this self-improvement loop, letting the models develop genuinely new ways to reason.
But this study kind of pumps the brakes on that. The whole point was to rigorously test that assumption. Is RLVR genuinely creating new reasoning abilities, or is it mostly just enhancing, maybe making more accessible what's already there?
Okay, so how did they go about testing that? What was the methodology?
Well, it was pretty clever. They moved beyond just looking at the first answer, that pass at one metric we hear about a lot. Instead, they focused heavily on the pass at k metric, using really large values for k, like giving the model many, many chances.
Okay, so sampling a lot more potential solutions.
Precisely. And they did this across different model families. Kun 2.5, Lemay 3.1 were mentioned, various RL algorithms, and a whole suite of benchmarks. Math, coding, even visual reasoning. They were really trying to find the edge, the boundary of the reasoning capacity.
So the core question boils down to, if you just let the base model try enough times, can it eventually match or even beat the RL-tuned version?
That's exactly it.
All right, before we get deeper, let's quickly hit the main takeaways for anyone needing the short version. What are the key bombshells here?
Okay, first big one. RLVR boosts performance when you only take one shot, pass at one, but often doesn't create fundamentally new reasoning power.
So it makes the model better at its first guess, but maybe not smarter overall.
Kind of. Second point. The base models, if you let them sample enough think pass at k with a large k, can often match or even outperform the RL-tuned models. Their potential is wider than we might think.
Interesting. What else?
Third, RLVR mainly seems to bias the model towards answers it already knew could be right, making it more efficient at finding them, but potentially limiting its ability to explore other solutions.
The efficiency versus exploration trade-off.
Exactly. And finally, distillation learning from a better model seems fundamentally different. It can actually introduce new knowledge and expand reasoning beyond the base model's limits, unlike RLVR in these experiments.
Okay, that's a fantastic quick summary. Let's unpack that first point now, the finding about pass at large k values. You said RLVR models actually did worse sometimes.
Yeah, that's the really counterintuitive part. When you crank up k significantly, giving the models lots of attempts, the study found that the original base models consistently started to outperform the versions that had gone through RLVR training.
Wow. And this wasn't just in one specific area.
No, it was consistent across the board. Math, code generation, visual reasoning across different model families like Quen and Lamona.
So the common wisdom that RL boosts performance, that's mostly true for getting the answer quickly, like on the first try.
It seems that way, yes. When you look at pass at 1 or low k values, RL often does help, but as you allow for more sampling, the underlying capability of the base model starts to shine through.
So the implication is, a base model, just given enough shots, might be able to solve problems we thought were exclusive territory for RL-enhanced models.
That's what the results strongly suggest, and they even did some manual checks on the chain of thought processes.
Where the model explains its steps.
Right, and those checks hinted that RL might sometimes even narrow the potential scope of reasoning, not expand it. It might prune away potentially valid, just less probable lines of thought.
Okay. That leads directly into the second key finding, which sounds crucial for anyone optimizing these models. RLVR boosts sampling efficiency, but reduces the reasoning scope. Can you break down how they showed that?
Yeah, they use Perplexity Analysis. For listeners maybe not deep in NLP, Perplexity basically measures how predictable a sequence is for the model. Lower perplexity means the model finds the sequence more likely, less surprising.
Okay.
What they found was quite revealing. The reasoning paths the RLVR models use to get correct answers. Those paths already existed in the base model's potential outputs, and often with, a decent probability.
So RL isn't forging new paths. It's more like paving the existing, making them easier to find.
That's a great analogy. RLVR biases the model towards those paths that got rewarded during training. So yes, it becomes more efficient. You need fewer samples, fewer tries to hit a correct answer.
But there's a cost.
Exactly. The trade-off, as shown in Figure 1 of the paper, is reduced exploration. The model becomes less likely to try different, perhaps more creative or unusual approaches.
Which means when you do allow for lots of attempts with a high K, it covers a smaller set of solvable problems compared to the base model that's still exploring more widely.
Precisely. The boundary of what the RLVR model can solve seems capped by what the base model could already potentially do. It's refining the search in the known territory, not discovering new contents of reasoning.
Okay, finding 3. Did they find that certain RL algorithms were better at maybe escaping this limitation than others? Like, is PPO different from GRPO or DOPO in this regard?
Well, they tested a bunch of them. PPO, GRPO, Reinforced++, RLOO, Remax, DAPO. The finding was that while there were minor performance differences, none of them fundamentally changed the score dynamic. They all seemed constrained by the base model's capabilities in the long run when looking at hike performance.
They introduced this term, sampling efficiency gap, or AERC. What exactly is that measuring?
Right, ASE. It's basically the difference between the RL model's pass at 1 score, its first shot accuracy, and the base model's pass at K score, way out at K256.
Okay, so it quantifies how much better the RL model is on the first try compared to the base model's potential after many, many tries.
Exactly. It measures how much efficiency the RL algorithm is adding compared to the theoretical upper bound set by the base model's full sampling potential. A large gap means the RL, while efficient, isn't capturing all the problems the base model could solve eventually.
And the result was?
The gap, ASEs, was consistently large across all the tested RL methods. You can see this in their Figure 7 and Tables 2. It strongly suggests that current RL techniques are still leaving a lot of the base model's inherent reasoning potential on the table, even if they make finding some answers faster.
All right, so RLVR seems focused on efficiency within existing limits. Now, the fourth finding contrasts this with distillation. How does distillation differ fundamentally?
This is a really important distinction they draw. While RLVR seems to tweak the probabilities within the existing model, distillation actually seems capable of bringing in new knowledge and genuinely expanding the reasoning scope.
How does that work? What's the mechanism?
Distillation involves training a smaller or base model to mimic a more capable teacher model. The paper uses the example of distilling DeepSeek R1 into Qwen 2.5.
Okay.
By learning from the outputs and maybe even the internal reasoning steps of that stronger teacher, the student model can actually acquire abilities and knowledge that weren't present in its original architecture or pre-training data. It's like getting lessons from a smarter entity.
So unlike RLVR, which seems stuck within the base model's initial potential, distillation can actually raise that potential by incorporating external, more advanced knowledge.
That's the key difference highlighted. Figure 6 in the paper shows this visually. The distilled model's pass at K curve can surpass the base model's curve, even at high K, which is something the RLVR models consistently fail to do in their experiments. It suggests a path to actually expanding reasoning capacity, not just refining it.
Let's really dig into the why now. Why might RLVR be failing to generate genuinely new reasoning? What are the underlying mechanics proposed in the paper?
They offer a few key points based on their deeper analysis. First, looking at specific problem sets like AME24 math problems and coding tasks detailed in Tables 4 and 5, they found the set of problems the RLVR model could solve was largely just a subset of what the base model could already solve, if you sampled enough.
So, no new problems unlocked, just a different selection of the existing ones.
Pretty much. And this ties back directly to that perplexity analysis we mentioned earlier.
Right, the measure of how likely the model finds a sequence.
Exactly. They compared the perplexity of outputs for the base model, the RL-trained model, and even a stronger model like OpenAI-01 on some AIM problems. Figure 6 shows this nicely. The outputs from the RL-trained model had a perplexity profile very similar to the base model's own preferred high-probability outputs.
Meaning the RL model isn't generating radically different novel thoughts. It's mostly picking from the usual suspects defined by the base model, just maybe re-ranking them slightly.
That appears to be the case. It's refining the probability distribution over pathways the base model already knew about, rather than forging fundamentally new ones. It optimizes within the existing capability space.
You mentioned they look at specific RL algorithms in more detail. Any practical takeaways there for engineers choosing between, say, PPO and APO?
Yes, Section 4.3 goes into this. Using their VRL framework and the OmniMath rule dataset, plus testing on Math 500 for generalization, they compared PPO, GRPO, reinforced plus pin, RLOO, Remax, and DPO. The main trend held none broke the reasoning boundary limit. But there were nuances. The APOs sometimes got a slightly higher pass at 1, but often needed way more training data and could sometimes perform worse at higher K.
Interesting trade-off.
Yeah. RLOO and Reinforce++ seemed pretty stable and effective overall. Remax showed some potential training instability, which is something to watch out for. So no single silver bullet, and some come with different costs.
What about just training for longer? Can you just brute force past these limits with more RL steps?
That's another angle they explored in Section 4.4, looking at the asymptotic effects using GRPO. The results were not encouraging for that idea.
Oh.
While pass at 1 on the training set kept going up with more steps, suggesting it was learning the training data better.
Right, potential overfitting.
Exactly. The gains on the test sets were marginal. But here's the kicker. The pass at 256 score, measuring that broader reasoning capacity, actually started to decrease with more training steps.
It got worse with more training. Why?
The hypothesis is that prolonged RL training further narrows the output distribution. It reduces entropy, makes the model less exploratory, and effectively shrinks that reasoning boundary because it becomes overly focused on the rewarded paths it saw during training.
So, if RLVR isn't the key to new reasoning, what are the fundamental roadblocks? Section 5 of the paper discusses potential limiting factors, right?
Yes, they draw a contrast between RLVR for LLMs and traditional RL successes like AlphaGo Zero or DQN in games.
What's the key difference?
Two main things. The absolutely massive action space in language-generating sequences of tokens is way more complex than choosing a go move and the huge influence of the pre-trained prior.
The knowledge baked into the base model, how does that limit RL?
Well, the prior is essential. Without it, the action space is too vast to explore effectively. The prior guides the model towards sensible outputs. But, they argue, it's a double-edged sword. The model is heavily biased by this prior knowledge. It's hard for the RL process to push the model significantly beyond these ingrained patterns. If it tries something too different from its prior, the output is likely to be low quality or nonsensical, get a negative reward, and the model learns to just stick close to what it already knows.
So the pre-training, while necessary, also acts like an anchor, preventing truly novel exploration via RL.
That seems to be the core argument. The prior constrains the exploration space. They even suggest maybe starting RL from a distilled model, which might have a better prior, could be a temporary workaround.
But ultimately, we need something more.
Yeah, they stress the need for new exploration techniques designed for this huge language space, techniques that can actually venture beyond the prior, and maybe exploring entirely different training paradigms beyond pure RLVR.
And how does this paper fit into the existing research landscape? They mentioned related work, I assume.
They do, in Section 6. They acknowledge the significant work already done, especially citing models like OpenAI O1 and DeepSeek R1, which really spurred a lot of this research, including open source efforts. They mention that others have noticed related things like RL models sometimes echoing base model behaviors, but they position their work as a more systematic, rigorous analysis, specifically focused on whether RL adds reasoning capacity beyond the base.
And their conclusion is more definitive on that point.
Yes. They go further by suggesting that perhaps all the effective reasoning paths found by RLVR might already be latent within the base model, which is a stronger claim than just observing some overlap.
Okay, so wrapping this up. For the AI researchers, the ML engineers listening, what's the big takeaway message from this deep dive?
I think the core message is RLVR is definitely useful. It's valuable for making LLMs more efficient at accessing the reasoning skills they already possess, finding the good answers faster. But it doesn't seem to be the mechanism for instilling fundamentally new, qualitatively different reasoning abilities beyond what the base model foundationally allows.
And the evidence was that base model performance at high sampling, large K, the perplexity analysis showing path overlap, the limitations across different RL algorithms, and that key contrast with distillation.
Exactly. Those pieces all point towards RLVR as more of a refinement and efficiency tool within existing capabilities rather than an expansion tool.
This really does raise a fundamental question then. Does this mean we need to rethink how we're trying to build truly advanced reasoning into these models?
I think it strongly suggests that, yes, relying solely on RLVR might hit a ceiling pretty quickly if the goal is superhuman or genuinely novel reasoning.
So what's next? Maybe hybrid approaches, combining RL's efficiency with distillation's knowledge transfer, or something completely different.
That seems like the million-dollar question this research leaves us with, doesn't it? Maybe those hybrid approaches, maybe entirely new learning paradigms. We need ways to actually expand that reasoning boundary, not just search within it more quickly.
It's a fascinating challenge. For anyone wanting to read the paper themselves, where can they find it?
The authors have a project page with the paper and other materials. It's at limit-rlvr.github.io. Definitely worth checking out if you're working in this space.
Excellent. A really crucial piece of research pushing the community to think critically about how we build smarter AI.
Absolutely. It provides vital clues about where future efforts might need to focus to really push the frontiers of LLM reasoning.